All right, welcome back. And today we are going to do a fundamental tree problem, a binary tree problem. So in here, we are going to do a question called balanced binary tree. So let's look at the question. Given a binary tree, determine if it is weight balanced. For this problem, a height. The height balance. A height balanced tree is defined as a binary tree in which the left and right subtrees of every node differ in height by no more than 1. Cool. So in case you don't know what a balanced binary tree is, it means that for every node in the tree, if you look at the left subtree, the height of the left subtree is either the same as the right subtree or it differs by only 1, right? So like for example, if in this example, this is a balanced tree, and in this example, it is not a balanced tree. So how do we do this? So this is a classic case of a recursive solution that we are going to do, okay? So let's look at the iPad. Let's just draw one tree here. 9, 20, 15, 7. To be honest, the numbers don't even matter because in this problem, we don't care about the number. We only care about how many nodes there are. So I'm gonna actually just erase these numbers to make it more clear. And then we'll just have nodes. Okay, so let's look at what height actually means. So here, the left height, I'll put L, would be 1 because this guy is a height 1. And then this tree is height 2. So right equals 2. Excellent, okay? So for this case, it's good. Oops, wrong color. So this is good, okay? And then let's look at this one. So here L is 0 because they don't have any children's for the left side. The right side also 0. So this guy is also good. And then this guy, L is 1 because this is height 1, and then R is also 1 because this is height 1. So because the difference is 0 or 1, this is good too. And then we have the same one here, 0, R 0, L 0, R 0. So these are both good. And then because all of these are green, this is a balance. A balanced diet. Okay, let's do the other case. So then the other tree looks like that. Let's draw it bigger. Like this, then like this, like this. So we can easily see that for here, the left subtree is 1, 2, 3, is height 3. And then the right subtree is height 1. So then this difference is way too big, so it is not a balance, so not balanced. All right, so how do you do that? So how would we do it in code? We could do it recursively, meaning we want to know if all our children are balanced, then the only thing we want to know is what is the height of my left subtree and what is the height of my right subtree. If one of the subtrees are in balance, it means I'm in balance. So we can already return false. But then if they're both balanced, it's still possible that, like for example here, they're actually both balanced. Like this subtree is actually balanced, and then this subtree is actually balanced. However, it is not a balanced subtree because the left one is way taller than the right one, okay? So let's do it recursively because like we said, if all our children are good, then we just have to check if left and right has the same height. So how would we do it? So recursion, what you do is you check the left subtree and then you check the right subtree. So first you're here, right? This is your call stack. And then you check the left subtree first, right? And then you check here. And then recursively, you're gonna check the left subtree. So you're gonna get all the way here, right? And then now you check this guy. This guy is definitely good because L is 0, R is 0. And then what you want to do is you want to pass back information into your parent function, the one that called you, and then pass in your height, which is 1. You're going to pass in 1. My height is 1. And also that I'm Gucci, as in I am balanced. So am I balanced? Yes. Oh, true, right? So now that it knows it's true, that's totally cool. What it's going to do is going to call this guy. All right. Now we're here. So is this guy good? Yes, it is good. It is balanced subtree because L equals 0 and R equals 0. And then it's going to pass back that height equals 1. So height equals 1. So what are we going to do for these heights? These heights are actually L and R. So here, L equals 1 and R equals also 1. So then because they are both balanced, both subtrees are balanced, this is also good, right? And then now what I'm going to do, I'm going to pass back the height to my parent. So I'm going to pass the parent 2. And then now this is L2. And then now it's going to call this guy. And then this guy is good also because the height is L0, R0. And then it's going to pass back a 1. And then R equals 1. So their difference is 1. So this is still good. So we're still good. We're still good. And then this guy is going to pass in a 3 because its height is 3, and also saying that I'm Gucci, all my tree is balanced. So now L equals 3, and then I want to know what my R is. So we're going to call this, is this a balanced tree? Yes, it is. Why? Because L is 0, R is 0. But I'm going to pass back a height of 1, so R becomes 1. So here you see that's the problem. L is 3, R is 1, difference is too much, and now we see that this is a bad subtree. Da-da-dum, da-da-dum. So yeah, it's dead. So we could have done it a little bit differently. I could make an example just to make sure you guys understand that, imagine if this guy was like here like this, right, like that, and then let's erase this guy. Imagine if it was like that. Then what would have happened is by the time we get to here, because here technically the height of my left subtree is 3, but then the right is also 3. But this would still be red. Why? Because here it would have been, once we got to here, it would have been red. And the reason why it would have been red is because here L would be 2, R would be 0. But because it's red, you're going to pass in your height, but also pass in that I'm not Gucci, like I am not a balanced tree, to your parent. And then once you have one of the subtrees say that's not a subtree, you are automatically infected and you become red. So here's a different case why it's red. Not because when you compare the left subtree and right subtree is bad, it's because one of your children are bad. They're not balanced. So yeah, so that's pretty much it. So all right, let's check out the code. Actually, before we check out the code, let's talk about what the time complexity is. So as you can see, we traveled through the whole tree, and for every node, we just visit it once. And how many nodes are there? There's O of n. So the time is O of n, and the space is constant. And the reason why it's constant is because we didn't add any data structure. We didn't malloc anything, so it's totally fine. Oh, actually, that is wrong. I tricked you. So the space is actually O of n. And the reason why the space is O of n is because you used recursion and you had the call stack. The call stack would be, the maximum call stack is how many call stacks you've been to. So as we can see, we did n. So it's actually the height of the tree. The height of the tree. However, you don't know if the tree is balanced. So it could very possibly be that the tree is like this, right? It's just a whole line. So because of that, the height is n, and there are n nodes. So that's why the space would be O of n, because the maximum call you can go is as deep as the tree. Kind of like when I went there, we said, oh, we're gonna call left, recursively call left. Each time you call the function, it adds memory space to the function call. So O of n would be the max. Yeah, if the tree's balance is actually log of n, but you don't know if the tree's balanced. The question asks you if the tree's balanced. All right, whew, that's cool. So now we're gonna do the code. So for this question, what we wanna do is we want to define a helper. Why do we have to define a helper? Because each of the recursive call, not only do we have to send in if we are balanced or not, we also want to send in the height. We want to give our parent the height. So we're going to have a new function, root. So this technically, what you want to do is you want to pass in a boolean and an int, right? Okay, so let's do that. And then if root is none, then what do you want to return? You want to return true, as in I'm Gucci, I am balanced, and 0 because you have no height, okay? So that is the base case. Always start with the base case for recursion. Now what do you want to do? You want to know if your left children are okay, if you want to know if your right children are okay. So left B, I'll call it, is it balanced? Left H, it means like what the height is balanced. Oh shoot, is balanced helper root left. Okay, did I spell it right? Is balanced helper, okay. And then right B and right height equals is balanced helper, and then you call that on to the right. And then once you have that, what you want to do is you return only true if the left is real. If the left subtree is balanced, and if the right subtree is balanced, and then also if the height difference is smaller than 1, so the absolute value of left height minus right height is smaller than 1, and also you want to return your height. You want to give your height back to your parent. So what is your height? Your height is the maximum of your left subtree and your right subtree, because that's the height, and then you add yourself, your own node. Yeah, so cool. So here is the boolean, right? Because when, like here in the base case, you say, oh, am I a balanced subtree? Well, I don't know. If all this is true, then yes, I'm a balanced subtree. And then what is my height? My height is the biggest, the tallest tree of either my left or right, plus myself. I add 1, and then that's pretty much it. And then what you want to do is you want to call that function balance helper, and then you just take the first element, which says am I balanced? All right, cool. So this works. Let's see if it works for everything. All right, perfect. So that's pretty much it. Very fundamental question on balanced trees, or in binary trees in general. And yeah, I hope this was helpful. See you on the next one.